So today's course is Introduction to Topological Concepts, and we'll begin by looking at the problem sheet which is dated 14th of March of 2020. Okay, so the first question is supposed to give example which of the following. So non-orientable compact surface with Euler characteristic 0, and so the answer to that first part, so we want an object which is non-orientable but with Euler characteristic 0, and that's a Klein bottle. Now we want a compact one-dimensional object which is not a curve. So the example I'm going to give in this case is a closed interval, and the reason being a curve is a connected one-dimensional manifold, and know that a manifold looks locally like the real line or an open interval. So now if you look at the neighborhoods of this point, there are some neighborhoods which will not resemble the open interval, namely the neighborhoods of the endpoints. Now a one-sided surface, an example of one-sided surface is Mobius strip. And in this case, you simply mean the Mobius band with the boundary removed. And then finally, for a topological invariant, an example of a surface, sorry, the example I'm going to give is a genus. We are required to reduce this word to a normal form word or the form MP, where M is some positive integer. And in each step we need to show the circulation rule which is used, and then eventually write the normal form word which is alternate to this. So now I will start is the following. Anytime when you see edge labels which occur in the same direction, think Mobius band rule. So we'll say that this is equal to. So now we want to apply the Mobius band rule here. So we'll say this is homeomorphic to A, B, C, C. But now when you apply the Mobius band rule, we'll bring this C adjacent to this and then flip the intervening block. So when you flip this, we'll have B, A, and so we say by Mobius band. So next we are going to apply the cycle rule, so that we start with this A followed by this A. So we'll start from here. And so we'll see that this is by cycle rule. Again, we'll bring this B adjacent to this by the Mobius band rule. So the purpose of rewriting this is just to make sure that there's a distinction in my steps. So now if you apply the Mobius band rule, what we'll have is the following. So now that is if you flip this block, and so we'll get that this is by the Mobius band rule. And so we are almost done, but now we want to make sure that if where possible all our edges do not have this superscript. So we'll say that this is equal to A, B. So we want to apply the flip rule to this block so that we get this A, B, B, and C, C. So this is by flip rule on the block. So now as you can see, these are three copies of the Mobius band. So we see that this word M is homomorphic to 3P. So now what is the alternate normal form word to this? So from our previous classes, we've seen that this is homomorphic to the connected sum between the Klein bottle and the projective plane, and it's also homomorphic to the connected sum between the torus and the projective plane. Okay, next we want to show that for a pattern this relation holds, and now to verify that relation we need to know the following. Now twice the number of edges is usually equal to 1, v1 plus 2, v2 plus 3, v3, and so on, where v1 simply denotes vertices of valence 1, this is the number of vertices of valence 2, this is the number of vertices of valence 3. The same expression for twice the number of edges is 1 f1 plus 2 f2 plus 3 f3, and so on, where f1 is the number of faces which are one side, that's one gone faces, the number of faces with two sides, that those are two gone faces, the number of faces with three sides, which is three gone faces, and so on and so forth. Now this relation holds for any general tiling. However, when you talk about patterns do not have vertices of valence 1, they also do not have faces that are one gone, and so our expression for twice the number of edges will be this, and also this one here. Okay, so we also need to know how to find the Euler characteristic. Now the Euler characteristic of any compact surface is given by V minus E plus F. But again, if you want to consider the number of faces, if you have faces of mixed types, then the number of faces in this case is F1 plus F2 plus F3 and so on. But again, remember that we do not have one gone faces, and likewise the number of vertices is V1 plus V2 plus and so on. But again, remember in this case we will not have vertices of valence 1. So to get that relation, we'll start by multiplying this expression for the Euler characteristic by 2. So we'll have twice the Euler characteristic is equal to twice V minus twice E plus twice F. So first of all, we are going to make use of this expression for the for twice the number of edges. So this is so the number of vertices will be V2, V3, V4, and so on, and twice the number of edges will be 2V2 plus 3V3 plus 4V4 and so on, and then the number of faces will be F2 plus F3 plus F4 and so on. So if we simplify this expression, this is 2V2 minus 2V2, which will give us 0. This is 2V3 minus 3V3, which will give us minus V3. 2V4 minus 4V4, which will give us minus twice V4, minus twice V5, and so on. Sorry, minus thrice V5, minus 4 times V6, and so on. Together with this expression, F2 plus F3 plus F4 plus F5 plus F6 and so on. Now next we are going to write the formula for twice. We are going to redo this, but this time making use of this alternate expression for twice the number of edges. So this will be, so the number of vertices will just be V1 plus V2 plus V3 plus V4 and so on. And then on this side we are going to add twice F2 plus thrice F3 plus 4 times F4 plus, this should be minus, plus F2 plus F3 plus F4 and so on. And now in a similar manner, if we take our difference, then what we are going to get, what we are going to get is the following. We'll get V2 plus V3 plus V4 plus V5 plus V6, and then once again we have twice f2 minus twice f2 plus 2f2 will give us 0, minus 3f3 plus twice f3 will give us minus f3. Now we'll have a similar expression, an expression similar to this, but for the faces. Now if you put these two together, if we sum up this, so call this 1 and call this 2. So if we take 1 plus 2, then we should be able to get the expression, the desired expression. So in other words, if you consider on the side of the vertices, we'll start with twice v2 because there's no v2 here. But now minus v3 plus v3 will give us 0. Minus v3 plus twice v3 will give us plus v3. Then minus twice v4 here will give us 0. Minus twice v5 minus 3 times v5 will give us minus v5. Then we'll also have minus twice v6 and so on. And similarly for the number of faces, the next question, you are supposed to describe how to construct a paper cylinder and a paper Mobius band. Then you are supposed to tell whether the two objects are isotopic and justify. And so for the first part, step number 1, you'll take a rectangular sheet of paper just like the one I'm having here. Then next you will bend it into a cylindrical roll and then glue the edges. So you have a piece of paper, you make it into a cylinder and then glue the edges, then you'll have your paper cylinder. Then for the paper Mobius band, the first step is that you will take a rectangular paper strip, but this time your paper strip should be longer between the top bottom edges than the right left edges. Then the second step, you are going to bend your paper into a cylindrical roll, but now before gluing you'll give your paper half a twist. And so if you do that, you'll have constructed a paper Mobius band. And so the question is, are the two objects isotopic? And the answer is no. The reason being, if you consider a paper cylinder has two boundaries. So there's this boundary here, and you also have this boundary here. But now for a paper Mobius band, so a paper Mobius band will only have boundary. In other words, if I start walking from here, I can go all the way around. And come back to the same position. So I just take a walk around and you'll find that this paper Mobius band has only one boundary. Now the last question requires you to explain what happens when you what happens to the twists and to the boundary of the Mobius band when you cut the Mobius band halfway from a node. So now that I'll leave for you as an exercise. You can maybe take your rectangular paper strip when you go home to construct a Mobius band. Just draw a line, maybe on both sides, which marks your halfway. Then construct a Mobius band and then try cut along this black line for my case and see what happens. But already I'm going to tell you that what you should expect is the following: that number 1, you'll get an object which has got twice the number of twists as a Mobius band. So it's not a Mobius band kind of, because a Mobius band should have just one twist. And then number 2, the resulting object still has one boundary. So you can go try that at your own practice session. And so I want us to stop there. That marks the end of our revision session for today, and have a wonderful time revising. Thank you.